Till now we have seen building blocks in combinational and sequential logic. Some of them are small circuits, not necessarily a building block and a circuit. There is no, for example, an adder can be called a building block if you want to build an arithmetic unit, and same time it is a circuit if you think of this as a connection of gates, interconnection of gates. So it is not a very rigid definition. The components, building blocks, circuits, subsystems, these are all freely used. Most practical systems, digital systems, are sequential in nature. Of course, a sequential circuit will also have a combinational part. What I am trying to say is very rarely do you have a circuit which is combinational, all combinational. Occasionally it comes like a code converter, parity checker. But mostly digital systems are combination of both combinational and sequential circuits. The sequential circuits, sequential components or building blocks are required to store let us say information. The information need not be always data. Information may be a state. A circuit remains in this state, then it has to go to another state based on which state it is in. For example, if you take a counter, counter is a sequential circuit. It counts from state to state, but then the count has to always to be retained in order to know what should be the next count. So a circuit remains in a called a state. This is called a state. A circuit remains in a state. A particular count is a state, and then when the input comes, it goes to the next state, which is the next count. Then we have the, take another example like traffic light control, light controller. Circuit has to remain in a particular state, let us say green on the main road and red on the side road. It's an intersection of a main road and a side road. Main road has a traffic flow, the green signal, side road has a traffic is stopped because of the green red light, and then it has to go from that to the state wherein we want to go briefly stop the traffic in the main road and let the traffic in the side road pass. So the circuit has to know which state it is in, how long it has been in that state, before you can make a decision whether it is time enough to sufficient the right time to change the sequence of lights. Of course, it may not go from red to green, green to red. It may go through amber or yellow, as they call it. So these are different states. So a circuit or a system, a digital system, need not be huge like computers and digital television or flight simulators, and can be even small things. That's what I mean. A traffic light controller, elevator control, a simple video game, counters. These are also systems. So whenever you design a system, we need to know what are the various states in which the system is permitted to be in, and what sequence of inputs or what input should occur for the system to steer from state to state. Generally these are called state machines. A state machine is a name given to a digital system. Today we will talk about state machines. This comes from the good old days of machines. Computer was called a computing machine, right? So everything was a machine. A state machine is a circuit which goes with a system or a circuit, whatever. As I said again, let us not be too specific about it. It has several states in which it can exist, and it is a clearly defined set of inputs which will steer the circuit or the system from one state to the next state. and each state it can also produce an output. So, let us think of this as a simple circuit in which there are 4 states. I call these states S0, S1, S2, and S3. So, this is the circuit or the system I am talking about. Now, let us say there is only a single input called x, which decides what state the circuit goes to from a given present state, and then it also produces an output z or z. So, I will call this input variable x, output is z, both of them are binary variables. So, it can only take a value of 0 or 1, output can also take a value of only 0 or 1, all variables are binary, there is no doubt about it. What I am trying to say is, if circuit is in S0, it will remain in S0, and when a input occurs, so a particular input occurs, it goes from S0 to S1 depending on whether the input is 0 or 1. I just assume that if x is 0, let us say the circuit does not go from that state S0, it remains in S0. On the other hand, if x is 1, it goes to S1. An example, it could be other way, or it can go from x is 0 from S0 to S3, SL1 it can go to S0 to S1, or it can remain instead S0 for x is equal to 1 and go here for x is equal to 0. These are all different possibilities based on the system you define. So, in each state of the circuit or the system, I look at the inputs, what are the inputs possible in that state, and what should happen to the circuit when the input occurs or does not occur. The input is true, what should happen? The input is false, what should happen? In S0, if the input is true, it goes to S1, if the input is false, it remains as X0. On the other hand, I can say, as a just for a change, I will say if it is x is equal to 1, I remain in S1, the circuit remains in S1, and it goes from S1 to S3. I am writing this sort of a random arbitrary way in order to tell you that these are also possible. Do not think that it has to go in a chain or anything like that. And from S3 it may go to S2 if x is equal to 0, and from S2 it may go to let us not even bother about what this system could possibly be. What is that this will be, what is that will be done by this system, what is that the circuit is going to realize. This is a concept I want to bring in, a concept called state machine. A state machine is a machine, of course a machine is, these days you do not call a computer as a machine. Any electronics circuit or system you do not call a machine anymore. Machine is, to us a machine is a big thing in which something has to move constantly and all that type of thing. High speed, you may call an engine a machine maybe, or an electrical machine, or a huge crane or something. You may call it a machine, but not a simple IC which is inside your computer. It is rather difficult to visualize this as a machine, but it is a machine in the sense it does certain things. A machine is a mechanized device. What is a machine? A machine is a mechanized or automatic device which does things according to certain pattern or design, according to certain design. If you accept that definition of the machine, that this is a machine, a state machine, why is it called a state machine? It is not a machine which takes the input and gives the output. It is a machine which can exist in several states, and output depends on the input and the state in which it is in. Only if you know the state in which it is in, then you can decide this input can lead to what next. What will be the next state of this machine can be determined only if you know the present state of the machine and the input in that state. And also not all machines need to have inputs, external inputs. A counter can just go from count to count by just by clock. Because we have a sequential circuit here, and all sequential circuits have clocks. So I will have to also assume there is a clock here. I may not have an external input x. Each clock cycle it may go from one state to the next state. A counter is one such. Supposing I have a 4-bit binary counter going from 0 0 0 0 to 1 1 1 1 and back to 0 0 0 0. So I do not need any input except the clock. With every first, suppose the circuit is in 0 0 0 0, the counter is in 0 0 0 0 state. At the first clock pulse it will go to 0 0 0 1 state, second clock pulse it will go to 0 0 1 0 state, third clock pulse it will go to 0 0 1 1 state and so forth, and the 15th clock pulse it will go to 1 1 1 1, and 16th clock pulse again it will go to 0 0 0 0, right. That is also a state machine because it also has states which moves from state to state based on the previous state. What we can only be sure of is the next state is determined by the previous state. There may or may not be external inputs in addition to the previous state information. So in order to determine the behavior of this machine or the system or the circuit, I need to know what state the machine is in now, what state the circuit is in now, and what input is likely to occur. And in that input, what are the options of the input? The input is 1, what will happen, or the input is 0, what will happen. And there may be more than one input. There may be 0 input, there may be 1 input, there may be 2 inputs. Then there are x1, x2 can be 2 inputs. Then x1, x2, 0, 0, x1, x2, 0, 1, x1, x2, 1, 0, x1, x2, 1, 1. There are 4 different conditions and 4 different states it can take next value. And it can also give you output other than the state. The state itself can be an output. A counter, for example, a counter is the simplest thing. The simplest state machine you can think of is a counter which there is no external inputs, no external outputs. A count is in state 0, that means the count is 0. There are only 16 states, a 4-bit machine, 4-bit binary counter, there are 16 states starting from 0 0 0 0 to 1 1 1 1. First state is 0 0 0 0, second state is 0 0 0 1. With one clock alone, without external input, it goes from state to state to state. Is there an output other than the state? No, the state output is same as the output. If the circuit is in state 1 0 0 0, I can say the count is 8. On the other hand, this circuit can have an external output in addition to the state in which it is in. In S0, Z can be 0 as an example. In S1, Z can be 0 again. S2, Z can be 1. In S3, Z can be 1 again. So the basic requirement of a state machine is there should be more than one state in which the machine can exist. There is only one state, that is the combination logic. You give the inputs, the output is determined. If more than one state is there, then it is a state machine. You may have several states, and the behavior of the machine can be determined by the path it takes from going from state to state. This behavior can be determined not only by the previous state or the current state it is in, but also by the external inputs. And in each state the circuit can give, in addition to the current state information, can also give you the output information which is different from the state information. For example, with 4 states I have to represent these 4 states. So, I can't have all the states as, so I have to, how do I distinguish between state S0, S1, S2, S3? I need to represent these states as again binary variables, binary. So, I can for example say S0 is 0 0, S1 is 0 1, S2 is 1 0, S3 is 1 1, the natural binary sequence. Okay. Now, since I was already used X and Z and S for this, let me call this A and B as the state variables. So, there are 2 variables called A and B. When A and B are both 0, the machine is in state S0, and at that time X becomes 0, it continues to be remaining 0 0, giving an output of Z equal to 0. If on the other hand, when the circuit is in 0 0 and the input happens to be 1, it goes to state S1 which is defined by this state 0 1, gives an output of Z equal to 0 again, and there again it is tested for X is tested, X is 1, it remains in the same state, if X is 0 it goes to state S3 which is called, which has a value of 1 1 for A and B and so forth. So, this is the state machine, and the representation of the state machine is called a state graph. Or a state diagram. Okay. Now, coming to this, if this state graph or the state diagram represents this system, it needs to have 4 states. 4 states are represented by 2 binary variables, because 2 binary variables can have 4 combinations 0 0, 0 1, 1 0 1 1. These 2 binary variables are denoted as A and B. So, I will know what state it is in by looking at the value of A and B. If A is equal to 0 and B is equal to 0, I know this circuit is in state 0, S0. If A is equal to 1 and B is equal to 0, for example, I know the circuit is in state S2. So, what are these A and B? These are A and B are the states in which the circuit is, and then this has to be retained. This will go to the next state. From this state, this will go to the next state after 1 clock period. So, what triggers this transition? Of course, the input will determine the transition, but what triggers the transition is the clock. Without clock, the circuit will not work. So, there is a clock here which triggers the state the state transition. The transition will be determined by the inputs. What transition will make will determine the input, but the state itself must be, just because you give the input x is equal to 0 here, it will not go here. If you give input x is equal to 1, the circuit is remaining in this state for this during this clock period, the current clock period, current clock cycle, and you make x is equal to 1, it will not jump to S1, it will go to S1 only at the next clock cycle. The clock triggers the transitions, inputs determine the transitions, and the state determines what output will be there. So, that means I need to have these variables A and B coming out of this. Since this value of A and B is required for me at least for 1 clock period, only then I can determine what state it will be in the next, because the circuit is just, let us assume the circuit has just now reached state S0 or S1, let us say circuit has just now reached S1 which is 0 1, and input of x is equal to 0 has occurred. it needs to go to S3 next. And I told you S3 it can reach only after the next clock pulse, at the next clock pulse edge if you want edge triggering. That means I need to remember the value of this S1 which is 01 for the entire duration of this clock period. Only then at the end of the clock period, at the beginning of the next clock period, the transition can happen from S1 to S3 because input x is equal to 0. That means I need to store the value of A and B in what? In what do you store the values? Bits are stored in flip flops. I need 2 flip flops to store the value of A and B. So I have an A flip flop and a B flip flop. And the value will be given to, let us say, are simple D flip flops, DA and DB. And since the circuit is in now state AB which is 0 0 or 0 1 whatever it is, and it has to go to the next state, the system should know the circuit is in this state and system should know this is the new input. That means I need to give this information back into this state. So I will modify this drawing, not use the clock here. So the A and B values are given back into this. This is the present state information which is held by the flip flop along with the input. Present state information along with the input, and then it will reach the next state after the clock edge. So I will use this clock here. So basically this, the whole circuit holds the whole scheme. This is the state machine or the digital system or whatever you want to call it, but this consists of 2 parts, very distinctly 2 parts. This is the sequential part which remembers the present state and makes it available for next transition, and this is only a transition circuit which determines what is the present state and what is the input, decides what should be the next transition. So this need not be sequential, this is only a combinational logic, because I need to know what is the present state and I need to know what is the input, so that I can determine what the next state will be. The determined value will be here, but it will not yet become the next state. It will become the next state when the next clock pulse arrives. At the next clock transition, this information will be moved on to this place, that will become the next state information, and the next state becomes the present state. The chicken egg problems, you know. You can either say the next state information is fed here, or you can say this is the present state and this becomes the next state. So what we will call it, this is the present state information. This is the input information already said. This is the next state information which is determined by the present state information and the input, also determines the output of the present state, but next state information is becomes the next state by absorbing these values into this flip flop, by storing these values in this flip flop. That will happen at every clock. At the next clock, this becomes next state information. The next state information becomes the present state for the next cycle, and then that will be corresponding with the input. It will go inside the third state and so forth. So, each state the circuit is in one clock period, the circuit is for one clock period the circuit is in one state. It is not necessary the circuit has to change state. If x is 0 for a long time, for several clock cycles, if we have x is equal to 0, the circuit happens to be in S0 and x is 0, it will remain in state 0, S0, right. Every clock pulse it will sample the input. During every clock transition, the input will be looked at, it is called sampling the input. The input will be looked at, okay, the input is 0, so I will remain here. Again next clock pulse it will say what is the input, 0, I will remain here. Next state pulse again I will see the input, 0, I will remain here. I remain here until you are not going to change your x, I am not going to move out of this place. And then suddenly you change your input from x is equal to 0 to 1, the next clock transition, okay, now you have changed, I will also move, go to S1. So, one transition corresponds to one clock period, but not necessarily every clock period if there is an external input. If on the other hand there is no external input, then every transition will lead to a new clock state. That is the counter example I told you. So, if I want to draw a counter state graph, a simple counter graph, I will make it a simple 3-bit counter. I don't want to go on drawing. So, let us say this is S0, no input, arrows do not have any condition attached to them, x is 0, x is 1, because there is no external inputs. So, this is a counter the only input is the clock, the outputs are A, B, C. Okay. Now, this is S0, S1, S2, S3, S4, S5, S6, S7. So, this is state 0, 0, 0, 0. Remember that I am notice that I am writing it outside the circle, not inside the circle. Back to 0, 0, 0. These are only state values, no? These are not outputs. Of course, you are treating them as outputs if you want to, but it is a state. If there is an external input, it is generally the external input is written inside the box, inside the circle. It is a convention. So, there are 8 states and it keeps going only with the clock. There is no external input, no external output. So, this system I am not defining x, I am not defining as z. These are 3 inputs and this ABC will keep going. Of course, this ABC will require to be fed back. This is a counter, so there is no need for this itself as this. Since I put 3-bit counter, you know that inside there is flip flops. I am not showing those flip flop model because there is no combinational logic here. The counter, you know how to build a 3-bit counter, right, using 3 flip flops. So, that is it. So, there is no question of one more. On the other hand, here since there is an external input and the current state variables, to determine the next state variables and the external inputs, external outputs, we need a combinational logic. The combination logic determines from the present state information and the external inputs, what should be the next state variables, what is the value of the next state variables and the output. There may be variations of this model, x may not be there, z may be there, x may be there, z may not be there, there may be more than one x, more than one z, all those variations are possible. More than two state variables, it can be 3 state variables, 4 state variables. But this is the generalized model of a state machine any digital system can be reduced to this block diagram. Of course, they are very, very complex. We are talking about a computer, talking about a missile launch system, or we talk about traffic control, it may not be that difficult. There are only 4 states or 5 states, 4 states in which it does operate. If you are talking about a water level indicator, if you talk of your washing machine, water level has to be indicated and then go to one state called water filling, maybe one state in which the circuit remains in that state several clock cycles the water until the water level becomes a particular level. So, x may be the input just to which will indicate the water level. As long as x is 0, that means not adequate level is reached, the water flow will continue. So, you can model any digital system, small or large, using this model of a generalized state machine. So, anything, even a counter is a state machine. Even a combination logic is a state machine with only one state, trivial case. A combination logic has only one state, or there are 2 states maybe in a single flip flop. Flip flop is a state machine, a single D flip flop is a state machine, 2 states q is equal to 0, q is equal to 1, right. Counter is a state machine, depending on number of bits, number of flip flops, I can have several states. On the other hand, this is also a state machine, it is a generalized model, a state machine. If you understand this concept, in order to design a digital system, all you have to do is to reduce it to a state graph from the behavior. Given a behavior of the circuit to you, you have to model it as a state graph. What are the various states? As I said, take the example of traffic light controller. What are the various states the controller has to be in? Let us assume there are 4 states possible. So, let us call this main road, it is called side road. So, main road has to be green, side road has to be red, this is going to be one state. Then main road will become yellow and still side road has to be red, second state. Then side road has to be, side road will become, main road will become red, side road will become green, correct, and then main road will become red, side road will become yellow, and then again it will go back. You can have a sequence without any control of, you can give a timer. Each state, my clock period can be so slow, let us say I want each of these states to be, let us say 30 seconds, because states are both of equal importance. So, let us say every 30 seconds it will change. So, I can, in principle, of course, you do not do a 30 seconds clock, you will have to get a faster clock and reduce it, I told you how to do that. So, if I have a clock which is changing state only every 30 seconds, supposing a 30 cycle period clock, for one clock period this will be in this state, next clock period this will automatically, this. So my state machine will be very simple. I call this S0, S1, S2, S3. This is MG, SR, so I will write GR, I will write YR. First is the main light, second is the red side light, then RG, then RY. And I am assuming a clock of, which is very impractical, clock of 30 seconds. Then there is no need for an external input and external intervention and all that type of thing. On the other hand, I may want the main road signal to be longer duration than side road signal. Main road green has to be 2 minutes or 1 minute, and the side road can be only 20 seconds. In that case, I should put a timer and then say, if the timer is 0, T1, I will call it T as the timer for the main road. Timer has not reached its value, it will remain in that state. If it has reached its value, it will go to this state. Here I will have to have a timer again, so I will call this T2, whatever, I want to call it T1, T2, T3. Yellow light has to be a fraction of a minute, no? About 10 seconds, 20 seconds. Then it has reached the limit, you go here, then this will be third timer. So I can have timer inputs, and when that time is elapsed, it will go to this, and this will remain for a period of T4. So I am saying this state will be for a period of T1, this state will be on for a period of T2, this state will be on for a period of T3. So I need external inputs which will give the timing events T1, T2, T3, T4. When the particular time elapses, T1 will be on, particular time elapses, T2 will be on, another time interval elapses, T3 will be on, and so forth. So I can now read the do the model as T1, T2, T3, T4. I need some more space for this, I will do it here. And I need outputs, there are external outputs called MG, SR, MG, MY, MR, SG, SY, SR. These are the 6 lights I need. And how many states the circuit is going to be in? How many states? And 4 states we need how many state variables? Because these 2 state variables can give you 4 states 0, 0, 0, 1. So I will call these state variables P and Q as the state variables and call this 0, 0 state, 0, 1 state, 1, 0 state, 1, 1 state. That means based on the present state information and the current value of P and Q, the next state information will be decided and which light will be on will be decided, right. So I will have to get this P and Q outputs into the 2 flip flops, D flip flops, dP, dQ, and take it back P and Q. So, I want to call this P plus and Q plus because the present value of PQ along with the present set of the time array information decides which should be the next value of P and next value of Q and what are the lights should be on, and this PQ information will be stored for one clock period and tested every clock period. So, what I am trying to say is whether it is a very simple system or it is a very huge complex system, you can reduce it to a state machine model. The state machine model is a machine in which the circuit will be represented by several states. The circuit can exist in several states. In each of these states it can give an input that need not output. It can give an output, need not give an output, and each of the states it check an input or several inputs. So, the next state of the circuit will be decided by the present state in which the circuit remains along with the external inputs. The next state information along and output will be determined by the present state information and the present state inputs. Trivial cases I already told you that no external inputs, but it is a state machine, is a counter. Again, trivial case example, there is no external outputs other than the state variable outputs is the counter. Counter does not have external outputs, only state variable as outputs, no external inputs except the clock. A combination logic is a trivial machine with no state, one state, no flip flop. A single D flip flop is a one state machine, two states on and off, or a traffic light controller, or this model, anything. Now, all we have to do is now think of various things you want to design, various systems and subsystems and circuits you want to design, and try to model the behavior of that into a state graph. So, a word description of the problem very clearly given to you as a specific set of specifications. The set of specifications has to be modeled as a state graph. Once you have a state graph, I can reduce it to this form. Of how to implement this we will have to see, of course. How do you make a state graph? How do you convert this into inputs required, what inputs will require and all that. So, how to implement this state graph, but the most important part is the state graph drawing. Once you are given the specifications of a circuit or a subsystem or a system, if you are able to reduce it to a state graph, rather not reduce it, represent it as a state graph, then the rest is easy, the life is very easy. So, the next few classes, I will teach you how to implement a given state graph. We will go later on into how to formulate state graphs based on specifications. Given a state graph, how do you translate into this? How do you translate this into this? How do you translate this into this? That we will have to first see. Then you have a tool, procedure. After that, all you need to do is to formulate the state graph properly for a given problem. You have to understand the problem specifications clearly and form a state graph, and if you know how to implement a state graph as a hardware, then you know how to build it, how to design it and how to build it and test it. So, that is in crux the digital system design theory, and this is called, these are all synchronous circuit, as I said, clock dependent. I said the states go from, the circuit goes from state to state at the end of the circuits are the clock triggers the transition of the state from one state to the next. So, this is called a synchronous sequential circuit. In an asynchronous sequential circuit, there will be no clock to steer. Some events will drive the next state. Suppose I am in a present state, you can define a particular event to happen, and that event will take it to the next state, and you define another event to happen, that will steer to the next state and so forth. That is a little more difficult to analyze as well as design. We will not do it now. So, first we will start with synchronous sequential circuits, wherein there will be a clock and always you can rely on the clock to work at the clock precision, as I said, clockwork precision. At the clock transition, the system will transit, system will change its state. So, all you have to do is to make sure that the new inputs, new values are put here before that, before the next clock pulse arrives. You take all the time in the earth and the world to determine the combination logic delay, because I am not going to do anything until the clock arrives, that only, then only it can go to the next state. Go on. So, we will see many examples in the coming classes. Do you have any questions on this generalized model of a state machine? Okay.